All right, so I'm going to solve this problem again, but this time we're going to use a little bit different of a method. I want to show you how you can actually transform impedances and voltages across a transformer to create a new equivalent circuit. So in this circuit, we're trying to solve for V out. So it would be helpful if we could transform this resistance and this voltage source over to the other side of the transformer so that we could just be left with a simple voltage divider, right? I could have my 32K here, my transformed resistance and my transformed voltage. But how in the world do I do that? That seems impossible. Well, it's not. This is actually one of the beautiful things about transformers is that you can do this. And so we know that when I go across a transformer, we know that when I go across a transformer, my voltage, we'll call it V1, if my turns ratio is given as N1 to N2, my voltage V2 is just V1 multiplied by the turns ratio, right? For the current, on the other hand, we know that I2 is equal to I1 multiplied by the inverse of the turns ratio, okay? So if we want to transform an impedance, or a resistance in this case, which is equal to V divided by I, we're basically transforming the voltage and the current, okay? And we can divide what happens to both of them, okay? So what we do is to transform an impedance, we have to do what we would do if we transferred the voltage, N2 over N1. So, sorry, let me just say R new is going to be equal to our R value, but we have to do what we would do in the numerator as if we were transferring a voltage, and in the denominator as if we were transferring a current. So N2 over N1 in the numerator, because that's where V, right, it's V over I. The V part is in the numerator, and the I part is in the denominator. And so I can say that this is equal to R times N2. I can multiply top and bottom by N2, so I get another N2. I can multiply top and bottom by N1, so I get an N1. And what I end up with is that my new R value is equal to my original R value multiplied by the turns ratio squared. And that is a really unique result, and that's exactly what we expect to see. And so what I'm basically saying is I can redraw this circuit now with my 12 angle 0 voltage. My resistor is no longer on the primary side. I've transformed it over to the secondary side, and it's going to appear right here as R multiplied by the turns ratio squared. Well, the turns ratio squared here is 4 squared, so that's 16. So this would show up as a 16 kilo ohm resistance. And now this resistor here is still 32K, and I'm looking for V out, right? That's the voltage that I want. Well, I know this voltage, V2, now really easily because V1 is just 12 angle 0, right? V2 should be 4 times that, or 48 angle 0. So I can say V out is going to be my input, which is 48 angle 0, right? I'm looking at this now as if it's just a voltage divider. I've got V2 here, that's the source of my voltage divider, and then I've just got a basic resistive network. So I can say 48 angle 0 times 32 kilo ohms divided by the sum of those two, which is 48 kilo ohms. That is equal to 48 angle 0 times 2/3, which is exactly what we got in the previous case. And so I can say that V out is equal to 32 angle 0 degrees volts, which is exactly what we got last time. And so this is a really powerful strategy for working with transformer circuits, because you can transform voltages, you can transform currents, you can transform impedances, and you can make your life solving the circuit a whole heck of a lot easier. So what we basically did was we took this impedance, this resistance, better yet, we multiplied it by the turns ratio squared in order to transfer it across the transformer to this position. So it gets removed here and added here. So our new circuit has no resistance here, but the transformed impedance here. And then it's very straightforward to solve. We could also go one step further before I skipped this step, but we could also just transform this voltage across the transformer as well and draw the full equivalent circuit as just 48 angle 0 with a 16K resistor here and a 32K resistor there, and we would get the exact same result, right? That would give us this result here for V out. And that's just me straight up taking this 12 angle 0, multiplying it by 4, and then just modeling it on the other side of the transformer. So now the transformer's over here, basically unimportant to us because what we're interested in is V out, and we've transformed both of our quantities across the transformer to the other side. Okay, so this is going to be a powerful tool for solving these transformer circuits. If you have any questions about this, please let me know. I know it's a little bit confusing. I was confused when I learned about this at first too, but essentially it's just taking the voltage characteristic of the resistor and the current characteristic of the resistor and transforming both of them. And when you do that, because one is V in the numerator and one's I in the denominator, you get this turns ratio on the top, the inverse of the turns ratio on the bottom, and you end up with the new resistor being the old resistor multiplied by the turns ratio squared. Okay, so I'm going to go ahead and end this video. What do I got in the next video? Oh, in the next video, we're going to start talking about auto transformers, which is just another sort of unique type of transformer. Nothing crazy, but we'll talk about those in the next video, and then we'll do an example on those as well.